Bueno, hola a todos, bienvenidos, bienvenidas. Mi nombre es Pilar Alda. Yo formo parte del laboratorio de genética y ecología evolutiva junto con Nicolás Bonel y Julia Pizá en el CERZOS. Y hoy vamos a estar dando inicio a esta serie de seminarios del CERZOS. Este primer seminario va a ser en inglés. Es francesa, así que vamos a estar hablando en inglés. Las preguntas, ya sea de manera oral o por medio del chat, pueden hacerlas en inglés o si quieren hacerlas en español, nosotros acá con Nico podemos
Hacer una traducción.
hacer la traducción. So, welcome everyone. This is the first seminar. Today we are going to present, to listen to Eloide Chapius. Eloide Chapius is a researcher from the MiVEGEC. The MiVEGEC is an institute that depends on the IRD, the CNRS, and the University of Montpellier in the south of France. And Elodie is an expert in quantitative genetics. And we are listening Elodie today because Elodie is we have a long-standing collaboration between this lab at the CERZOS and her lab at the MiVEGEC. So, Elo, you can start. The floor is yours.
Thank you, yeah. So, sorry if I'm doing it in English because I don't speak Spanish. So if you don't understand, don't hesitate to tell me. As she said, I started my PhD in Switzerland in a freshwater snail. And that's where I started to understand what is quantitative genetics. And then for my postdoctoral position, I did 2 in Montpellier in France and pursue my knowledge of quantitative genetics. And I hope that during those 3 examples with freshwater snails, I will try to explain and convince you that using quantitative genetics for studying adaptation, invasion, and emerging infectious disease is important. Ah, super. It does not work. Oh, yeah. So at first, what is quantitative genetics? So when you look around you, you can see that there is a huge variation between species, but also within species, and even between individuals. And those differences are mainly due to the environment of the genetics. So the quantitative genetics wants to know what is the genetic part of this variation. And most continuous traits, so used in quantitative genetics, are coded by multiple genes, what we call a complex genetic. So the start of quantitative genetics could be done mostly by Fisher infinitesimal theorem by the beginning of the 20th century, who describes the variance of phenotype, so you can see here, is mostly due to variance of the genetic part and the environment. So it may look simple, but it's really complex. And 2 key concepts exist in quantitative genetics, so the heritability. It is the genetic part among the phenotype you can see, and also the breeder's equation. So it's an equation describing among the quantitative genetic part and the selective. So you can, knowing the phenotype of the parents and the selective pressure, you can estimate the phenotype of the offspring. So it was mostly done in a selective program like for crops or livestock. So the main things is to remove these these environmental variance is to make measure in a lab. So you measure really the genetic variance. So I will mostly get interested in what we call life history traits. So what are life history traits? It's traits that are linked to life cycle, so linked to fitness. So it's mostly growth, reproduction, and survival. So it's mostly when you start breeding and when at what size, when do you reproduce, how many offspring and when they survive, and how do you grow, and finally how many times, and how will you survive and disperse. So the obvious thing is that you can see that between species you can imagine variation because they live in different environments. But this variation also exists within species. For instance, between so on life stage, I'm talking about adult and juveniles, you can imagine that they are submitted to different predators. So the different the trait would be have a different phenotype. So because of the resource allocation and because the resources are limitless, all traits cannot be maximized. And there is a trade-off between traits. So one famous example is the trade-off between the quantity and the quality of the springs. So what we call the K selection and the R selection. So K here, K is for carrying capacity, and R species, so R strategy, R is for the growth rate. So it means that in unstable environment, our species have a tendency to go faster, to mature earlier, and to have less offsprings. Whereas in K species, in a stable environment, individuals have less offsprings, but they survive better. So as a recall, when you have many population linked with gene flow, it's what we call a meta-population. And in this meta-population, we have mainly 4 sources of variation. So, I mean, mutation, migration, drift, and selection. So the 3 first are what we call neutral, so they are not linked to selective events. So when you observe a phenotype, you want to know, is it neutral or is it due to selection? And for this, we have a method called FST-QST comparison. So the FST is a distribution of the molecular variance between population. So it's based on allele frequency amine, so it can be microsites. So it varies between 0 and 1. So 0 means that the population are not differentiated at all, and 1 that population are differentiated at maximum. So QSC is the same, but based on quantitative traits, so continuous traits. So both are, as you can, both are can be explained. Migration and drift can both be explained, but only selection with we be on QST. So anything that QST is different from FST is due to selection, where you can In the other word, when QST equal FST, just alone can be responsible for the pattern. You cannot say if there's selection or not. So when QST is different of FST, you can have two cases. So QST is lower than FST. So in these figures, UFST is represented by the pictogram lines. So the optimum of the population are the same in every population. So that's what we call an homogenizing selection. And at the opposite, you can have a QST bigger than FST. So this time you have a differentiating selection between population. So one apartheid is why do I focus mostly on snails? So I have a big variation in life rates. So in growth, in reproductive output, and in survival. And the main thing is also the mating system. So most snail species are hermaphroditic. And when they are male and female together, either they can be outcrosser or selfer. And this is important for the following. The ecological importance. So most species can be prey, predator, herbivorous, or on, and they also as one of the biggest invader groups of the world. And also to finish, they have a medical importance. So many species of snails can carry parasitic organism. So to finish, the breeding capacity of the snails is great. So we know how to breed them. And they have mostly a fast generation. So that can allow experimental evolution or quantitative measure. So the first example I want to show to you is an adaptation to an heterogeneous environment. So for this, I work on during my PhD, I work on the freshwater snail, so Galba trungatula. So it's a snail present in Europe, but also in Argentina. And it's mostly known because it's the main intermediators of a disease caused by the trematode Fasciola hepatica. And the second thing you have to know that it's mainly selfer. So the neutral variance is relatively low between population. And the last thing interesting that this species is present in two kind of environments. So one permanent and one temporary. That those two environments are differing by water persistent throughout the year. So temporary habitats can suffer from drought during the year. So what I did is that I sampled 17 population in Switzerland. So 7 from temporary habitat and 10 from permanent habitat. In each population, I collected about 13 individuals. Then I made what we call a quantitative genetic design. So by measuring 10 to 15 families per population. So what we call family is a genetic device by population. So we know the breededness of brother and sister. So here, the variance between individuals of the same family. So we think that we are in a clonal design due to the high selfing rate. So the variance between individuals is only due to the environment because we all think that the same genetical identity. And the genetical variance is the variance between individual, well, family in the same population. So just remember that all those variances are valid if we made only individual values. So I could calculate the QST between habitat and also FSC between habitat that I measure with the individual brought back from the field. So doing the QST-FSC comparison, I showed there is local adaptation between those two habitats. So I have FST almost null and QST relatively high. So here I show you QST for age of maturity, but you have to know that it's true for many traits. So to show you phenotypically some traits, so individual, so in blue here, individual from temporary habitat, sexually mature, older, and at a bigger size, but are less fecund. And we wanted to know why we have this difference between habitat. And the main thing it's between habitat is the amount of water you can have throughout the year. So we made a resistance to desiccation experiments. And what we can see here, so the border line is an individual from temporary habitat, and they survive more, a lot more than individual from permanent habitat. And taking into account several traits, we show that the bigger size can help to survive. So it could explain why individuals in temporary habitat are bigger. So the second example is also to understand the biological invasion. So again, for this, I took a community of freshwater snail in Guadeloupe. So Guadeloupe is a French West Indies island in the Caribbean Sea. You have a community of about 30 individual species, I mean. So you have a native, invasive, introduced species. So introduced, like Marisa was introduced to get rid of Bionfalaria elevata because it was a disease spreader, which I will explain after. So there is, in White Guadeloupe, there is more than 2,000 spots of water in the island, and we follow about 250 sites for more than 20 years, for almost once a year, and we measure abundance of the species and also presence and absence. So I focus on a couple of snails. So as you can see, you have two snails that really like. So Aplexa marmota and Phisa acuta. So Phisa is an invasive species, and Aplexa marmota is a native species in Guadeloupe. So the native is really badly touched by Phisa. As you can see, the density here of Aplexa marmota is really impacted by when Phisa acuta is coming. So as I said before, so as we can follow the site almost every year, we know precisely the date of arrival of Pfizer acuta. So you can see in the table here that we have population never in contact, and then you have in contact since 2010 and 24. So we have a population from different history of invasion. So I made at first continuous continuous analyze between both population, and then we compare only two types of population, what we call naive and inexperienced population. So naive was a population not invaded or recently invaded by the Pfizer acuta. Inexperienced was population invaded for more than 2 years by Pfizer acuta. So to show you phenotypically, so it was the same kind of design as Gelbart and Cazuela. So individuals from experienced population, so invade, tend to be sexually mature earlier, but die earlier and have a bigger fecundity. So at the same, we wanted to know why we have this difference. And the main thing you think at first is that native species change their trait to compete better with Pfizer acuta, which was not the case. So we made some experiment about competition between the two species, and what we can see here, that she lost almost every time. So you see the number of outputs, so it's the offspring produced by the species. It's always smaller in La Plexa marmorata. So she doesn't change her trait to resist to competition, but we rather think that it's a fugitive species that will escape from Pfizer acuta and try to have other niche. So the last thing I want to talk about is infectious disease, and now quantitative genetic can help us to know the genetic basis, and so expect the spread of disease and the control. The last example I want to take is the case of Bionflaria albatra. So one freshwater snail I talked to you before, and which can be parasited by schistosoma, and they cause what we call schistomasis. So it's a disease where the snail, you can see, as the independent host, and the definite host are mammals or human hosts, and they directly penetrate the skin to be fast. So what my colleague from Perpignan, so in France, wanted to do is try to have a control of this disease. So what they did, they brought back some Bufalaria from Brazil that was infected it can be infected at more than 50%. That's what the line we call L. And they selected experimentally two kind of lines, so resistant line at 90%, so called the R line, and the S line means you are susceptible. So you can be infected a lot by schistosoma. And the thing we wanted to know is that this resistance or this susceptibility is there any trait measure that can explain this difference? Can we see a difference? So I decided to make the quantitative genetic design and to measure like 20 traits between those 3 lines to see if we have a difference. So it was mainly the same thing as before. So the only thing we have to remember that this species is outcrossing, so not sulfur like Alprexa marmorata or Galba truncatura. But individually, I measure several traits. So to show you, for some traits, I have no differences between lines. So as you can see here, so it was the age and the size that majority. But for some traits like fecundity or number of eggs per capsule, we have bigger amount of eggs for susceptible for resistant line that's susceptible. So the last thing I want to show you, so it's still in progress, that's why it's kind of messy, that maybe for the we have an interaction for traits, between traits, I mean. So when we look for example, for growth, so we have a difference at the, you can see here the growth line between two selective lines. And we have a difference between resistance and susceptible lines at the end of the growth curve. So we have to think that maybe we have traits together that working different between lines. So that's suggesting a resistance cost. But we are still ongoing this work with a colleague that is making mathematical models to look at this. So that's it.
Thank you, Elodie. Thank you very much. So, does anyone have questions? I have some questions, but if someone has, you can put your questions in the chat and we will translate it if you want. Or you can make your question in English.
Or you can start, Billy, asking your question.
I have a question, Elo. I don't remember your paper about Truncatula.
Yes.
How many microsatellites did you use there in those papers? Do you remember?
7 or 8, I think.
7 or 8.
Right.
And
Okay.
that's okay. And that, do you think that's a good number? There's a good number of microsatellites to use to estimate the FST, or do you think that it's I don't know,
I
minimum?
think, but tell me if I'm wrong, that maybe it depends on the species you use, and since the Galba is mostly no variance at all between population, I mean using 7 or 15 microsat won't help much, but maybe I'm wrong.
It will be okay. Okay. And I have another question about your last experiment about Bionfalaria. So the resistance, if I understood well the picture, so the resistance will put more lay more eggs than susceptibles.
Yeah.
Okay.
But
And
they
you know
survive
why?
really
Do you have
badly. I think they lay many eggs, but the survival among earthlings and adult stage is really, really bad. So it seems that there is a trade-off between survival and reproduction. But why they reproduce more, I don't know why.
Okay.
Elo,
It's
I have one question. Yeah.
Yeah.
I
Sorry.
have one question related to this. Have you corrected the number of eggs by the size or weight or whatever?
No, because there was no really much difference between the maturity size, as you can see here. So no, I didn't,
Okay.
because the difference was not significant between.
Okay. So you found that the female fecundity from the resistance was higher than the.
Yeah.
Okay. Okay, nice.
And,
Maybe I bring you. I have some questions as well. Maybe I will bring you to the beginning of your presentation, which is
Yeah.
common for all of people that is doing common garden conditions. And you were talking. You were saying that to remove the environmental variance, we need to perform. We need to raise the individuals or the experimental lines in common garden laboratory conditions. And I was wondering how many generations do you need, do you think we need to raise to effectively remove the environmental conditions?
well, effectively, we say that the second generation is better, but it's really difficult to have some second generation for many species. So,
Okay.
but yes, it's better. For
Okay,
my
so
experiment, for instance, it was only the first generation.
Okay, yeah.
Because for Galba and Trongatula, raising two generation is really difficult.
Yeah, anyway, what we included in the statistical model. Because it will be the same, I guess, for maternal and paternal effects that might affect
Yeah.
that we can
But
drag it for.
in
Yeah.
Galba Truncatula, I estimate, but I didn't show you, but estimate that there was no maternal effect because I had no effect, no really big difference in what I call early traits. So
Okay.
traits on the beginning of the life stages, like growth at birth, growth before sexual maturity. So that's why I really estimate there is no maternal effect, but I'm not sure it's really true. When I
Okay.
say you remove, I mean you always have environmental effect, even
Yeah. We try to minimize somehow yeah,
just
exactly.
yeah.
So regarding because you were talking about the size and how do you measure size by measuring the length, the shell length, or weight?
I can show you for the Bionflaria, but it was the same. Do you see? You see my slide?
Sí.
Yeah.
Yeah.
So I measure the length and the weight of the
Okay.
weight, I mean, of
Okay.
the individual. So for Galba, it was the same. I measure the total length of the shell, but also the biggest weight.
And you did it directly on the microscope. You did it.
With my not for Bionfalaria because my binocular was not equipped, but with I do it in English, a micromètre oculaire, a
Okay.
micrometer in
Okay.
the eyes. So I did
No,
this.
when you say that some individuals are estimated size at maturity or age at maturity, sexual maturity, How do you know that they are sexually mature or mature? Do you
Because
observe or what, or just
for
by?
Galba and Plexa, so it was easy because it was a selfing. So as soon as you see an egg laying, you say it
Okay.
was sexually mature. And for Bionflaria, I made some crossings, so they were together in some aquarium, as you can see here.
Mhm.
And then I remove individually in boxes, and then when I saw egg laying, I see, okay, they are sexually mature. But you have to do this before they're really mature to be sure. So I started, but maybe they were 4 weeks old or something, to be sure, not to miss.
Okay, yeah. No, I got it because now we are trying to estimate for Ruminant decolata, which is a land snail. It's quite difficult to estimate the sexual maturity because there is no previous knowledge on that.
Ouais.
The age. So we are open dissecting them. So I thought that maybe you did the same, but
No,
yeah.
no.
No, okay. Okay.
Sorry.
Does anyone have some question?
Yes,
Hola, Alicia.
hola. Very nice presentation. Thank you very much for sharing with us your interesting results. I focused in your first example. I'm sorry, I don't remember the species name.
No, it's fine, Galba truncatula. This one? Yeah.
Yes. Galba truncatula. I was thinking about first, did you find a variation in chromosome numbers along species collect?
No, so me, I never look at that, but I think there is nothing found. Maybe I'm wrong, but I think nothing was done with sexual chromosome. No, Billy? I
No,
don't think.
nothing. No, nothing has been done regarding chromosome in Galba, within Galba.
Okay. And microsatellite data was in agreement with so high percentage of self-fertilization?
You have when you see the map, so when you are they're so selfing that the alleles are almost fixed in one population. So they can be really close and really strongly differentiated with the FST. You understand what I mean? So
Yes.
it's not linked to the geographical distance. It can be really high between two populations really close.
Mm-hmm. And also I was thinking, talking about adaptation. Maybe we also consider plasticity or just selection on genetic variation.
Well, as I said with Nico, as we made all my measure in the lab, we know it's not phenotypical plasticity because the environment was the same for every individual and every habitat. So it's only genetical. It's not phenotypical plasticity for sure.
Okay. Thank you.
You're welcome.
So if there's no more questions, we will close this seminar. We will thank you very much, Elo, for this presentation. Um,
I know it is hard
Mhm.
to ask questions soon after the talk, but if you have any questions and you want to contact Elodie, I don't know, Elo, if you put your email there, or you can,
maybe you can put your email at the
Or you
email
can-
address at the chat.
yeah, you can write us,
Yeah.
and then we can give you your her email address.
Mhm.
So don't hesitate. Ilo is not only working with the snails, she also worked with nematodes and other organisms. So she has plenty experience in experimental design, quantitative genetics. So don't hesitate to ask any question or contact her for whatever you think might be interesting.